Okay, let's show the example 2.12. Show that the integral from 0 to infinity x to the power of negative c over 1 plus x dx. This integral is equal to pi over sine of pi times c, pi c. Here, if c is between 0 and 1. Alright, so if we want to use the complex analysis to present this integral, we are going to define, or we need to define the complex function z to negative c. And z to negative c in the complex analysis is an exponential of negative c times logarithmic function of z. We use this way to define the general power function. And because we have this logarithmic function, so there's a terminology. This point z equal to 0. Z equal to 0 is called a branch point of this z to power negative c. Actually, it's a branch point of a logarithmic function, but here, since we focus on the z to negative c, it's also called the branch point of a z to negative c. And the integral will be called the integration around branch point, whatever. And this part, whenever you have a logarithmic function, you're going to choose a branch. You're going to cut the complex plane. In this problem, we will cut the complex plane in the following way. We have a complex number c, so that z is not equal to 0, and the argument of z is between 0 and 2 pi. So basically, this argument will tell us how we define or how we cut this complex plane. We cut it by this way. We will have complex plane, and then we remove the origin and the positive x-axis. We remove the origin and the positive x-axis. So the argument is strictly from 0, but not equal to 0, to 2 pi, but not equal to 2 pi. So we cut the positive x-axis. And when we have this cutting, we will get the logarithmic function L of z equal to, by definition, log r plus I theta. For z is equal to r e I theta, and theta is between 0 and 2 pi. Right? The modulus times e to I theta. Okay, so with this, we can define f of z as a z to negative c. Negative c is an exponential negative c L of z, logarithmic function, log of z. So we do have the solid definition. And then let's see how we construct the closed curve. The closed curve is constructed by the following way. So we do have an inner smaller circle centered at the origin with radius r. We call it gamma r. And we will have similar a bigger external circle centered also at origin with radius capital R. This is little r, this is capital R. And they are not closed. They are connected by a horizontal segment. The top segment we call it L1. The bottom horizontal segment we call it L2. Okay, these two circles are not closed. They have opening. And the outer exterior circle, we call it gamma capital R. For the exterior circle, we choose counterclockwise orientation. You see, counterclockwise, and then you reach the L2. L2, you go from right to left, and reach gamma R. Gamma R, you go clockwise orientation. You reach L1. L1, you will go from left to right, back to gamma R, capital R. So let gamma be gamma capital R plus L2 plus gamma little r plus L1. Right? So what is L1? L1 is Z. Z is equal to X plus I here. This height of L1 is delta, I delta. X, remember X connecting those two segments. X is between, actually it's it's between R and capital R. Strictly speaking, it's a little bit smaller than capital R. It's smaller than capital R because capital R is this point. Any other point will be smaller than capital R, and a little bit smaller than little r. It's not that straight. Okay, it's not that straight. And L2 is Z equal to X minus I delta, the lower than the x-axis. Here X is also between R and the capital R. Okay, so gamma little r, gamma capital R are connected by L1 and L2. Are connected by L1 and L2. Okay, so from this construction, we see the gamma is homotopic to 0 in G. Homotopic to 0 in G implies it's homologous to 0 in G. So we can apply the residue theorem. Check the condition of residue theorem. We need the homologous to 0 case condition. Okay, gamma is homotopic to 0 in G, and now let's check the residue. The residue of what? The residue of integrand f of z over 1 plus z. 1 plus z we can write like z minus -1 dz. No, dz, integrand. Z equal to -1. This is the residue. Residue, this is a simple pole. For the simple pole, residue is simple. You just remove the trouble factor from the denominator and evaluate. This is f of -1. F of -1, where's f? F is here. So it's an exponential negative log -1. Log -1 is R is 1, log R is 0. Theta is a pi, I pi. It's e to -c I pi. Okay, the residue of the integrand with respect to -1 is equal to e to -c I pi. Okay, then by the residue theorem. By the residue theorem, we have integral along gamma fz over 1 plus z dz. Here we put the coefficient of 1 over 2 pi to the right side. It's 2 pi I times the residue. The Wanting number is 1. The Wanting number is 1. So here we want to make sure that the -1 is inside this. So we will assume this little r is less than 1, is less than capital R. So little r is there. So the -1 will be inside this closed curve. Right, and the Wanting number is 1, so you don't have other multiplication. So it's e to -c I pi, I c pi, c pi I, whatever. Okay, so that is the residue theorem. That is the residue theorem. Now let's do the further discussion based on this conclusion. So gamma has 4 components. Let's study the integral along each component one by one. right? So let's see, the integral f of z over 1 plus z dz along L1, It is from little r to capital R, f of t plus I delta, x, that's actually x, 1 plus t plus I delta dt. Okay, so if we expand it, let's see what happens if we expand it from little r to capital R. F t plus I delta, so it's an exponential negative c log. You will have log c plus I delta, right? Plus I delta over 1 plus t plus I delta dt. You just follow the definition of f of z. Okay, so this becomes integral from r to capital R. Exponential negative c log, that's not log c, it's log t. It's log t, it's log t. So it's you will get t to negative c. So this part will get t to negative c, and times exponential of negative c delta and I. This one, exponential negative c I delta, I, and over 1 plus t plus I delta dt. Right? So this is a real part, the real part of a log function and the imaginary part of a log function. So this one is, we're going to claim this one is close to the t to negative c 1 plus t dt. So when delta approaches 0, this one will approach 1, this one will approach 0, they disappear. So we want to claim they are very close. How do we claim they're close? We check the difference and absolute value of difference. So this is the reason in the textbook you have the following argument. So it say let g of a t delta be defined on the compact set R capital R cross 0, 1/2 pi by what? I'm checking the difference. So g of a t delta is equal to absolute value f of t plus I delta no, this one's no, you have to write this like square root of t plus I delta times ei theta. Theta is a function of a t and a delta. Then it becomes exponential negative c log square root of t plus t square plus t square plus delta square, t square plus delta square, and plus I theta. Yeah. Sorry, this is not correct. Definitely is not such simple. So the formula will be extremely ugly. So this part, it becomes okay. Let me finish this and I will correct this. Minus t minus t to negative c over 1 plus t. Okay, let me correct it here. My argument is not correct. F is defined by the logarithmic function. Logarithmic function requires requires the modulus times EI theta formula. So theta is a function of t and delta, and then f of t plus I delta becomes exponential negative c log square root of a t squared plus delta square. This is numerator. This is a real part, I theta imaginary part. So it is equal to this function square root of t squared plus delta squared. This is a base to power negative c, and times e to negative c I delta theta, ci theta, and the theta is a function of a t and the delta. So it's extremely complex. So the function looks like this. So square root of a t squared plus delta squared to the power of negative c times e to negative ci theta of t delta over 1 plus t plus I delta dt. So it should be like this. Not that simple. That's incorrect. Okay, this one is incorrect. And again, we want to make sure that this function, this integrand, is very close to this one. Okay, these two are very close, but clearly we don't want to write it in such detail. So the author did not completely write down what is f of t plus I delta. They just want to compare them. All right, so we have this one. Okay, so that's the correction for my mistake. We have this function defined gt delta like this. This delta is greater than 0. Remember, this delta cannot touch, the delta cannot be 0. If delta is 0, you will make L1 along the positive real axis. So delta cannot be 0 for f of z. If you have f of z, you cannot say, oh, well, clearly delta equal to 0. This also makes sense. It does not make sense, because if delta is equal to 0, L1 is on the x-axis, positive part of x-axis. In that case, the logarithmic function is undefined. Okay, delta can't be 0. And what happens if we define this equals 0? So when delta is greater than 0, we have such definition. And when delta is equal to 0, we don't have additional formula. We just directly define it to be 0. Right? When delta is equal to 0, we just give it 0. And from those formula, you can actually see that, from those formula, you can see that the function gt delta is continuous. All right, the gt delta is going to be continuous from above. You see here, it's between 0 and 1/2 pi. It's from above. Okay, so you got the continuous function over the closed interval cross another closed interval. This is a compact set. Hence, G is uniformly continuous. G becomes uniformly continuous. Uniformly continuous, let's see. So, given epsilon greater than 0, there is a delta 0 greater than 0 such that for square root of t minus t prime squared plus delta minus delta prime squared less than delta 0, whenever these 2 points are close enough, we have gt delta minus gt prime delta prime the distance is going to be less than epsilon over where? R. You don't need really over R or over not, but this is just make the future writing beautiful. All right, and remember that we sorry, we have delta could be 0 when we have delta prime equal to 0, then this condition will have the following application. When delta prime is equal to 0, we have t delta, this is a point, the distance between t delta and the t0 is less than delta 0. T delta and t0 less than delta 0. Then what we get? We get the distance gt delta minus gt0 less than epsilon over r. Right? Here, this is t. T could be whatever t. So t is between little r and capital R. And gt0, remember gt0 is 0, so ops value is less than epsilon over r. This implies gt delta is going to be less than epsilon over r for t between r and capital R. It will be extremely small. And what is the delta? What is the condition of delta? Remember, this condition, t minus t is 0, so this term disappears. Delta prime is 0, so this term is 0. So this is square root of delta squared is less than, so you just get delta less than delta 0. Okay, this condition comes from here. Square root of t minus t squared plus delta minus 0 squared less than delta 0. And delta, remember, is a positive number, so this square root of delta squared is delta, so delta is less than delta 0. So this is what you can get from that. In particular, you have such a thing. It comes from this computation. Okay, so it's always less than this one, then the integral from r to capital R, gt delta dt, gt delta dt, it's by the inequality, it's less than epsilon r times r minus r is less than epsilon, right? So we get less than epsilon. The condition you see here, a t is integrated, so you only need delta less than delta 0. You only need this condition. All right, so for every epsilon, you can find a delta 0 such that when delta less than delta 0, this integral is less than epsilon. You take the limit. Hence, the integral from r to capital R t to negative c1 plus t dt is the limit. Delta approaches 0 from right-hand side. Be careful, this is from top. Integral along L1, fz over 1 plus z dz. This is our equality. We finally show that even though we have such complex expression, but when delta approaches 0, it is actually, it converges to the integral from little r to capital R t to negative c over 1 plus t. All right, so from top it will converge to 0, and from bottom remember the argument will converge to 2 pi. The argument will converge to 2 pi. All right, so when that argument converges to 2 pi, you will have similar computation. Check that similar computation. Try to see if you can get it. So similarly, we can have the integral from r to negative r t to negative c over 1 plus t dt times negative e to negative 2 pi I c, negative e to 2 pi I c. You see here, that's why you get it. And limit delta approaches 0 from right. Remember that is a minus delta. And integral L2 fz over 1 plus c dz. All right. Okay. And check here. This is z. This is complex conjugate. Z and the complex conjugate. But they are, when the z approaches 0, complex conjugate, z approaches a positive x-axis. Complex conjugate will also approach positive x-axis. But there's a small issue. Here, the argument approaches 0. Here, the argument approaches 2 pi. So there's a minor difference. There's a minor difference because we cut the branch, so you have like a river, you cannot pass the river. Okay, so that's what they write. The log of complex conjugate of z is log of z complex conjugate, but you have to plus 2 pi I. All right, so with this property and almost identical process, you can get exactly the formula like this. All right, so check what we have. We have integral over 4 pieces. Now we compute 2 pieces. We have the other 2 pieces. So the total integral is 2 pi I e to negative I pi c. And minus, you see, this is 2 integral, the integral over 2 p's. So it 1 minus e to negative 2 pi I c, the integral from r to capital R t to negative c, 1 plus t dt. It is, this difference is equal to the integral, but here remember we have to let limit delta approaches 0 from right side. Then the integral along gamma little r fz over 1 plus z dz. The integral along gamma capital R fz over 1 plus z dz. All right, it's a subtraction. You move 2 integrals to the other side. Okay, so this part we still don't let little r approach 0, capital R approach infinity. So we don't have them so far. Now let's see. Okay, now let's study those 2 integrals. They are both integrals along gamma with certain radius. So for whatever radius, rho is greater than 0, rho is not equal to 1. We let gamma rho be the part of the circle z modulus equal to rho from square root of rho square minus delta square plus I delta. So it's exactly like from here. Go clockwise. Okay? It doesn't matter you go clockwise or counterclockwise. Remember, we're going to put the modulus. So counterclockwise, clockwise will just generate a negative sign. With the opposite value, they disappear. To square root of rho square minus delta square minus I delta. So just get like this, a capital C shape. Okay, so the every point on this circle has a radius rho. Okay, that's important. Radius rho. Theta, I don't know. Theta has a complex formula. Then what? Then let's check the integral along gamma rho fz to 1 plus z dz. Of course, by the inequality fz 1 plus z modulus dz. Fz, remember we had that z is equal to rho ei theta. Theta is a function of rho and delta. So log z is log rho plus I theta. And so the f of z becomes exponential of negative c log rho minus ci theta. It is exponential negative c log rho. It's a rho not negative c e to negative ci theta. And once you put opposite value, it's equal to rho to negative c. So this numerator is equal to rho to negative c. And similarly, you see, if rho is less than rho is less than 1, this is a 1. Rho is less than 1. I'm sorry, it's bad. This is a rho. This is 1. If rho is less than 1, so every point z, let's use negative 1. Rho less than 1, negative 1 is outside it. Every point z plus 1 modulus is a z minus negative 1. That's the distance between z and the negative 1. Every point z and the negative 1, their distance is greater than z minus negative 1. This point. This is negative rho. Negative rho minus negative 1, right? It's greater than or equal to negative rho minus negative 1. If rho is less than 1. If rho is greater than 1, the same thing. This is rho minus, this is z minus negative 1. Z minus negative. So it's still this point. This is negative rho. This is negative 1. So the distance z minus negative 1 distance is always greater than or equal to negative rho minus negative 1. Either way, it is equal to, this one is equal to 1 minus rho. So it's greater than or equal to, put in the denominator, it's less than or equal to opposite value of rho minus, 1 minus negative rho. 1 minus negative rho. Okay, that's a little bit geometry. A little bit geometry here. Okay, so this is a constant, then it is equal to rho to negative c over opposite value 1 minus rho times 2 pi r. R is a rho, 2 pi rho. So this rho works for little r, also works for capital R. And this computation is independent of doubt. It's independent of doubt. So what we get? We get this whole thing is going to be less than or equal to 2 sums. So this 2 pi I e to negative I pi theta minus 1 minus e to 2 pi I theta integral r to capital R t to negative c plus 1 plus over 1 plus t dt is going to be less than or equal to what? Less than or equal to or put opposite value. I have to put opposite value. It is less than or equal to this one, first one. Little r negative c 2 pi r over 1 minus r. Capital R negative c 2 pi r over 1 minus r. 1 minus capital R. Okay. Let's see, if r approaches 0, remember that this one is r 1 minus c 2 pi over opposite value 1 minus r. R approaches 0, it will approach, the denominator will approach 0, enumerate is a number, smaller number with a positive power. It will converge to 0 times 2 pi is 0. R approaches 0, you get this limit 0. Capital R approaches infinity. Capital R approaches infinity. We're going to write this way. So R over modulus R minus 1 modulus ups value. This will converge to 1. And then you have 2 pi. And then you have R to negative C. This part, it has a negative power. You're going to flip it. So this converge to 1, 2 pi, and this one converge to 0, also 0. So both will converge to 0, then these two will equal, right? So 2 pi I e to negative I pi theta is equal to 1 minus e to 2 pi I c from 0 to infinity, t to negative c over 1 plus t dt. All right, so that's this. So what do we get? We get the integral from 0 to infinity, x to negative c over 1 plus x dx is equal to this 2 pi I e to negative I pi c is, I miss a negative sign, I think. Here, negative sign, yeah, I miss a negative sign. Over 1 minus e negative 2 pi I c. When multiply top and bottom by ei pi c, so 2 pi I, numerator cancel, denominator is ei pi c minus e negative I pi c. And we got pi I, over, not pi, 2i, ei pi c over e negative I pi c over 2i. Check here, this is by the Euler identity, this is exactly sine pi c. So you get the pi over sine of pi c. Oh, okay, finally we got the answer. Okay, so this is a little bit complex example, and this is the last example in this section of singularity residue theorem. And the application of residue theorems in the integration part is always a tricky one. Okay, so you must do more practice and try to get the idea how they come up with here or there. But in most cases, the closed contour is a creative point. You may not be able to get that creative point in possibly 10 or 20 minutes in the exam. So you have to memorize some stuff. All right. So let's see. Okay, yeah. Let's see one more exercise. This is from exercise 1B. Exercise 1B. They ask you to compute the integral am I right? Yeah. Yes. So well, let's do this exercise. Usually the complex sine cosine function in this residue part, we're going to use the exponential function to replace. So we will define f of z to be the e to iz minus 1 over z squared. Okay, and remember we're going to get the we're going to get the closed contour. It's like the sine x over x. So what we do, we possibly will do something like this. The big radius capital R and small radius little r. Okay, and then the interval from negative r to negative capital R to negative r, positive r to positive capital R. Okay, so let gamma capital R be REIT. T is from 0 to pi, and gamma little r be REIT. T is from pi to 0, opposite way, and interval negative capital R, negative r, and r capital R. Gamma is gamma capital R union negative capital R, negative r, union gamma little r, union little r capital R. So we do have a closed path. And then with the gamma is homotopic to 0 in the domain of the function, right? Homotopic to 0, then it is a homologous to 0. So we get, and there's no winding number. Sorry, there's no pole. The pole is excluded. The pole is 0. It's excluded. So this is 0. This integral is equal to 0 by the Cauchy theorem. Okay, so the integral has 4 pieces. So let's compute them part by part. Okay, so when you have the z along the x-axis, z is just x. So we will eventually use x to represent. So this is a EIX minus 1 over x squared dx plus from r to capital R EIX minus 1 over x squared dx. And clearly you're going to use the substitution x equal to negative u to transform negative capital R, negative R to be positive capital R, positive R. So use the u transformation, you will get negative r capital R, negative capital R, negative r e to negative iu minus 1 over negative u squared is also u squared. So it's a du, and there's a negative sign. X negative. And the second one, just copy it. And negative sign will help you to flip this capital R, positive R. So you will have little r to capital R. And just flip them to cancel negative sign. Then you have 2 functions. 2 functions have the, or you can just write the same variable. So you have e2 ix plus e2 negative ix minus 2 dx, minus 2 dx. And this one is twice of a cosine of x. It's 2 cosine of x and minus 2 over x squared dx. All right, so it's a 2 cosine x minus 2. All right, so that's the computation we can do along the x-axis. Let's see the computation along the capital R, gamma capital R. On gamma capital R, let's compute EIZ minus 1 z squared dz. It's from 0 to pi. Z is where is it? The z is here, so it's a EI r cosine t IR sine t, it's e minus 1 over r squared e2 it. And dz is r e I t I dt. And then you cancel r e I t. numerator I times this, so it's e to negative r sine t, I square is negative 1, and plus I r cosine t, and minus 1. Denominator, you cancel 1, you just have r e I t, and times I dt. Correct? Okay, then we put ops value. So ops value integral along gamma capital R e negative I minus 1 z squared dz is going to be less than or equal to integral 0 pi. You put the ops value into the integral. This one has modulus 1, this one has modulus 1, so you don't have them, you just have r. Denominator is r. Numerator is ops value of the difference. Ops value of the difference, you put the triangle inequality, so you get e, ops value of e to this. This is ei stuff, it's, the modulus is 1, so it's a e negative r sine t and plus 1 dt. Alright, use the triangle inequality. First eliminate this and put the ops value on the numerator. Numerator triangle inequality, get modulus the first one plus modulus second one. Modulus first one, you only need the real part, e to negative r sine t. Alright, so sine t, t is from 0 to pi, sine is positive, so r times positive number, negative, this is negative number. So it's less than 1. 1 plus 1 is 2. We're talking about positive numbers. Okay, so then what we get, this is a 2 pi over r. It will converge to 0 as r converges. R approaches infinity, it will converge to 0. So that this term disappears. Okay, now let's see the other one. On gamma little r. On gamma little r, we are talking about the similar thing. Let's see eiz minus 1 over z square. Eiz by the Taylor series expansion. What is this? This is a 1 plus iz plus iz square over 2 factorial and so on, and minus 1 over z square. 1 cancel. The first term becomes iz over z square, right? It's iz over z square, and plus this term, z square cancelled, is actually negative 1/2. So you see here, this is the important part, the polar part. This is the polar part. So we're going to claim this function is almost this function. So how do we do that? We're going to check the difference. We're going to check the difference. In this one, you see, after you subtract this, it becomes a Taylor series, a power series. A power series is an analytic function. So this function has a removable singularity. At z equal to 0. Each of them is undefined at 0, but after subtraction, it is an analytic function. So it's a removable singularity. And the removable has a removable singularity at z equal to 0. So there exists m greater than 0. You check the argument in the sine z over z. There exists a constant m greater than 0 such that the difference, this is the difference of them, will be less than or equal to m for z close to 1. Modulus of z is less than or equal to 1. So the integral of it will be less than or equal to m. You put it into it. It's m, integral of m along that one. It's a pi little r. It's a half disk, half circle. So it's pi r, not 2 pi r. and this converge to 0 as r converge to 0. Okay, so we have another limit equal to 0, but this limit is not the limit we want. We want this. So the integral gamma r e I z minus 1 over z squared dz limit r approaches 0 is equal to the limit r approaches 0 integral gamma r I z over z squared dz. All right, the difference converted to 0, it means the limit of those two integrand are equal. Why we do that? Why we do this process? Because this one I don't know how to do it, but this one I know how to do it. This is I over z. Z is from pi to 0. I over r e I t d r e I t I dt. Right? So this I over z, this is a dz. This one is dz. R cancel, EIT cancel. You got I square. I square is negative. R square is negative 1. So this I square negative 1. And 0 from pi to 0. Remember this gamma little r is from pi to 0. This is equal to pi. This one is equal to pi. Equal to pi, then so what we get? We get the integral, those two pieces. It is this 2 cosine x minus 2 over x squared dx, and plus this piece along gamma capital R EIZ minus 1 z squared dz over the gamma little r EIZ minus 1 z squared dz. Alright, and we're going to choose limit little r approaches 0, capital R approaches infinity. Okay, capital R approaches infinity, this term converges to 0. This one will converge to the twice of the required stuff, and the whole thing is equal to 0, remember. And this one, it will approach to pi. This twice of it plus pi is 0, so we get integral from 0 to infinity cosine x minus 1 over x squared dx is equal to negative pi over 2. Right? So that is my answer. Okay, so the exercise of this part are more or less tricky and constructive. So try to do some of them. If you have questions, we may discuss those questions. If any step has a mistake, try to make sure which give you the which part, which idea you missed or you misunderstand. All right? Okay, thank you.